So at the end of the last segment, I left you with a question. How do we know whether P1 and P2 are stable or unstable equilibria? And now I'm going to take you through 3 ways to go about determining whether these are stable or unstable. So to answer this question, what's critical is to look at the feedback loops associated with each individual equilibrium state, and also to keep in mind that for a stable equilibrium, after a perturbation, the system returns to its original state, whereas for an unstable equilibrium, after the perturbation, the system goes to a different state. For instance, from a state that's covered in daisies to a state that is characterized by bare earth. First method I'm going to take you through is a very intuitive method. It's just basically thinking about what happens to the system as you move it away from its equilibrium conditions. So let's consider P1 just to start out with. It's as good a starting place as any. And think about what happens when we perturb it to slightly hotter temperatures. Well, at slightly hotter temperatures, you see that conditions are more ideal for the growth of daisies. So we would end up growing more daisies, which would reflect more incoming solar radiation, and decrease temperatures. So we would have to move back in this direction on the x-axis. So we would, again, approach that equilibrium point. This means that P1 is a stable equilibrium. And to confirm that, let's just look at what happens when we perturb temperature in the other direction, when we perturb surface temperature to lower values. Now, at lower values, conditions are less suitable for the growth of daisies. So fewer daisies occupy our planet. Our planet is darker, has lower albedo, and absorbs more incoming solar radiation, which warms it up. So we again would approach this equilibrium point. So yes, indeed, we have a stable equilibrium at P1. Let's now consider what happens around P2. So here, if we perturb the system away from that equilibrium, you'll see that conditions, so if we increase temperature, conditions become less suitable for the growth of daisies. So fewer daisies grow on this planet, the albedo decreases, and it absorbs more incoming solar radiation and becomes warmer. So we move right along the x-axis. In other words, we move away from that equilibrium. This indicates that P2 is an unstable equilibrium. And again, to confirm that, let's look at what happens when we perturb P2 to lower values of temperature. So as we perturb P2 to lower temperatures, conditions become more suitable for the growth of daisies. We grow more daisies, we reflect more incoming solar radiation, and the planet becomes cooler. So we move to the left along the x-axis. In other words, we move in this direction away from P2. So yes, we have an unstable equilibrium. Now, the other option, so another way in which we can evaluate whether P1 and P2 are stable or unstable equilibria is a little bit more methodical. It's actually to reproduce the coupling diagrams around each of these equilibria. So if you recall, when we talked about the coupling from daisy coverage to surface temperature, there was a single direction that applied to this whole curve. So this whole orange curve is characterized by this coupling diagram, which I'll draw now. So as daisy cover increases, more incoming solar radiation is reflected away and surface temperatures decrease. So this is a negative coupling relationship. The black line, remember, represents the coupling from temperature to daisy coverage, and that coupling changes sign depending on which side of the optimum you're on. So over here on the right-hand side, we could draw a coupling diagram from temperature to daisy coverage. So as temperatures increase here, daisy coverage decreases. Again, we have a negative relationship, a negative coupling, whereas the coupling is the opposite sign on the left side, represented by the positive slope that you see here. As temperature goes up, conditions become more suitable for the growth of daisies. and we have a positive coupling. So in the vicinity of the P1 stable equilibrium, we have, we could just fill in our coupling diagram. I'm trying to determine where to do this, so let's do that over here. So P1, we have our temperature, we have our daisies. So there's a positive coupling from temperature to daisy coverage, which we get from here. And then from this, we get, there's a negative coupling from daisy coverage to temperature, which we can depict as so. And so we have a +1 multiplied by a -1. So +1 times -1 gives us a -1, which is a stable equilibrium. So this is a negative feedback. Which is associated with stability. So stable equilibrium. As you might expect, the opposite thing happens over here in the vicinity of P2. Let's just go ahead and draw that out. So again, we have our temperature, we have daisy coverage, and from temperature to daisy coverage, you see from here is a negative coupling. Whereas from daisy coverage to temperature is also a negative coupling. So we have a -1 times a -1, which gives us a +1. So this is a positive feedback, which is destabilizing. So our equilibrium is an unstable equilibrium. Okay. And then the third way is to think about these perturbations somewhat intuitively, but to actually draw what happens on the graph. I'm going to use a different color for this. I'll go ahead and use blue. So in the vicinity of P1, if we perturb the system to hotter temperatures, you could pick any one of these curves to go off of, but let's just say we're looking at the curve that represents the coupling from temperature to daisy coverage. So if we go to hotter temperatures, we have higher daisy coverage. So let's just say we start out over here. And so then we want to figure out what impact that actually has on temperature. So we could draw a line that goes across here. So at this particular value of daisy coverage, we have a fairly low temperature. And low temperature is associated with low daisy coverage. I'm going to switch to using the line function because I'm having a hard time drawing straight lines here. So low temperature is associated with low daisy coverage, and then we have to figure out what the impact of that particular value of daisy coverage is on temperature. So we could go over to this line to read that off. And then, so this low daisy coverage is associated with high temperatures. High temperatures are associated with this particular value of daisy coverage, and that value of daisy coverage is associated with this particular temperature. And so you see, if I drew my lines all perfectly straight, we would actually end up back at that equilibrium. This is probably the most challenging way to go about determining whether an equilibrium is stable or unstable, but it does end up working, and I'll leave this to you to play around with a little bit. So just to complete this little table here, we have that P1 is a stable equilibrium. And in the vicinity of P1, surface temperature to daisy coverage is a positive relationship. So it's a positive coupling. Whereas daisy coverage to surface temperature is a negative coupling. It's a negative coupling throughout the whole range of temperatures. So this is a negative feedback loop. Whereas P2, and let me just add that this is a stabilizing process. Whereas P2 is an unstable equilibrium. Because at P2, we have this relationship, a negative relationship from temperature to daisy coverage, and a negative relationship from daisy coverage to temperature. So this is a positive feedback loop, which is destabilizing. So let's consider now what happens when we crank up the sun's luminosity, because recall, we're not just solving for the equilibria of the system under a constant value of luminosity, but actually the sun is getting hotter, and we're trying to figure out whether this planet is going to become a hothouse or whether it is going to maintain some sort of stable equilibrium. So let's go back and draw our original two curves here. So we have our coupling from temperature to daisy coverage. Remember, this is hump-shaped with an optimum. And then we have our coupling from daisy coverage to temperature. So that looked a little bit like this. And then we have P1 over here and P2 over here. So this is our base case scenario. Now, what happens if we crank up the sun's luminosity? So you could think of the problem as such. When you crank up the sun's luminosity, the planet is going to be receiving increasing amounts of solar radiation regardless of what the daisy coverage is. And so for a particular value of daisy coverage, the surface temperature is going to be hotter. So we could simply translate this line upwards, which I will do in red. So this now represents the coupling from daisy coverage to surface temperature under a more luminous planet. So this red line represents our increase in luminosity. Nothing changes about the relationship from surface temperature to daisy coverage. Daisies still grow at the same optimum temperature, and so we don't need to do anything to the hump-shaped curve. What we do need to do, though, is make note of our new P1, which I'll call P1 prime, and our new P2, which is P2 prime. So what we see here is that there has been a slight increase in the equilibrium, in the stable equilibrium planet of our temperature. So there is a slight difference. Let me just choose a different color here to write this. There's a slight difference between P1 and P1 prime. So I'm going to call this the change in the equilibrium, or the TEQ value of our planet. Now, one thing that you'll notice is that if there were no daisies on this planet at all, or let's just say that there is no feedback from temperature to daisies. There's no coupling from temperature to daisies. So let's just consider a constant value of daisy coverage. So under constant daisy coverage, without this coupling, what you would see is that the increase in temperature would actually be much larger than TEQ. So that would be this value. So I'm going to call this delta T and F. So delta T and F is the change in temperature if there is no feedback. So if temperature had no influence on daisies. More in the next video.